Welcome, welcome, welcome. In this video, we're going to be discussing symmetries of a square. So, what does the word symmetry mean to a mathematician? It means we're going to take our object, in this case a square, and either rotate it or reflect it so that it returns to its initial position. So we couldn't take the square and rotate it by just 1 degree because it wouldn't return to this position. But you could rotate it by 90 degrees. That would be a symmetry. Now, for our activity, it's going to be a really good idea to get out a piece of paper and cut out a square. So let's say this is the square that you cut out. Now on that square, I want you to label the corners. Label the corners on both sides A, B, C, and D in that exact way. Now I did say both sides. So for example, if we take this square and we pick it up and we flip it over this vertical line of symmetry, we would get something that looks like that. So maybe this is the front side and that's the back side of your piece of paper after you flip it over that vertical line. So it turns out there's 8 different ways that we can perform this symmetry. So first we'll start with rotations. So you can rotate by 0. That would just leave the A, B, C, and D exactly where it is. So it's rotating by nothing. If you rotate by 90, the A would go right there. If you rotate by 180, the A would end up there. And by 270, we end up there. Now filling in the rest of the letters going clockwise, we would get. So those are our rotations. Now, there are 4 more reflections that are possible. So above, we already performed the vertical reflection, which puts A, D there, and B, C right there. A horizontal reflection would flip the top and the bottom. So A and B would come down, and the D and C would come up. In the downward diagonal reflection, the A and the C stay put, and the D and B switch places. Finally, in the upward diagonal reflection, the D and the B stay put, and the A and the C switch places. Okay, so one thing to note before we move on, these 8 symmetries that we've just shown on our page are ways of moving the square. So we're going to be working with ways of moving our square as opposed to like the square itself, at least mathematically ways of moving the square. Now, this has a really cool application. You can actually take a Rubik's Cube, a very complicated problem to solve, and mathematically represent all the movements of a Rubik's Cube and change it from like a visual problem to a mathematical algebraic problem. Now we're not going to do that for this course, but it's just giving you some of the powerful ideas that we're creating when we talk about symmetries in this way. All right, so one of the things that we're going to try to do is return back to the place that we started with our motion. So let's take V for example. So if we do our vertical reflection, so A ended up right there and D ended up right there, how would we return back to where we started? So how do we undo what V did? And we're only going to allow ourselves to work with those 8 symmetries. So everything that we do has to come down to those 8 symmetries. Those will be the objects that are in our set. So it turns out if we look closely, what we want to do is perform another V to bring us back to where we started. What gets flipped on the right gets flipped back to the left. So a common symbol to represent what we're doing is to invert it with a power of -1. So undoing V is represented by V raised to the power -1 And in this case, that would equal v itself. To undo v, you just do v again. Now let's remember that we always need to think of our symbols in their proper context. So raising to the power of -1, if we had numbers, like if we had 5 raised to the power -1, that would be the same as 1/5, or take the reciprocal. Now it turns out with multiplication, taking the reciprocal does produce the inverse, but here we have to avoid that type of thinking. We have to think of this symbolism here just means undo it, or more formally, take the inverse. So we don't think of 1/v. That doesn't make any sense in this particular context. Okay, so what about rotating by 90 degrees? How would we undo that? So maybe we'll track A. So notice A has landed right there in the top right. So if A is landed right here and we need to rotate it back to where it started, we would actually need to rotate by 270. So that's what undoes 90 degrees. So we can say that 90 raised to the power -1 in the context of this lecture is actually 270. Right? The only objects that we have are the symmetries. And here when we write 90 and 270, we don't mean the number 90, we mean rotating the square by 90 degrees, or rotating it by 180 or 270. Okay, so now that we've built our set of 8 different motions on the square, we can now introduce an operation to perform on those elements of our set. Our operation is going to be called then do. And simply put, it means do one thing and then do the other thing afterwards. And for simplicity, we're going to drop writing then do every time because it will get a little bit tiresome to keep writing then do over and over and over. Just like when the context of our multiplication is clear, we don't write the multiplication symbol every single time. We're going to pull that same trick here because in the context of this lecture, we're only talking about symmetries. So we're dropping the then do symbol for simplicity. Okay, so how would this look like in practice? So if we did a V and then we did a 90, so first we would do our vertical reflection. This side switches with that side and we end up there. And then we would do a 90-degree rotation. So the A would end up down there, and then it goes around D, C, B. And then from the A, we have D, C, B. So we've correctly done the V and then done the 90. Okay, and we can also think about undoing multiple motions of our square. So we could think about how do we undo a V and a 90? Or in terms of our mathematical language, what does V then do 90's inverse equal? Okay, so what we want to think about is how do we go in the opposite direction? So if we start right here, how do we go back to the beginning? So maybe we'll think of these arrows going in the opposite direction. So if we wanted to go backwards, let's think about how we undid 90. Well, that was a 270. And how did we undo V? Well, we just performed another V. So that's exactly what we do to find this inverse when we put it all together. So first we do a 270, and then we perform a V afterwards. And that's exactly what occurred here. So if we track the A like we've been doing before, we rotate it 270. The A started down here and it went 1, 2, 3, all the way around to the top right. And then what's on the right-hand side flipped with what's on the left-hand side, and we've performed our V. to get back to where we started. So in algebraic notation, what we can write, the inverse of V90 is 270 and then do a V. So finding the inverse of V90 is the same as doing the inverse of each individual symmetry in the opposite order. So here's a playful way to visualize that. Let's say you're getting ready to go out for a nice night. You might first put on your socks and then put on your shoes, but to undo that whole operation, when you come home, it's first shoes off and then socks off afterwards. So I'd also like to share with you a very nice tool for performing then-do operations with the symmetries of a square. So this tool is called a Cayley graph, and the idea is to break everything down into a single rotation or a single reflection. So for our picture, what we'll do is draw a 90-degree rotation represented as a blue arrow with just one direction towards that arrow. We'll draw a red double-headed arrow for a vertical reflection. Okay, and then we'll think about all of the ways that we can travel from one symmetry to another using these symbols, either the blue or the red. So from 0, if you start at 0 and you rotate by 90, you get to 90. If you do another rotation by 90, you get to 180. Another 90 to 270, another 90, back to where you started. Okay, and if you're at 0 and you do a vertical reflection, you land at the motion of V. So you might have to take out your square and play with different possibilities of performing the red arrow, which represents the vertical reflection, or the blue arrow, which represents the 90-degree rotation. See if you can fill in the rest of the Cayley graph by pausing the video now. Okay, so after a little bit of effort, you should have found that rotating V, so after you've performed the vertical reflection, if you rotate V by 90 degrees, you end up at U. And if you rotate U by 90 degrees, you end up at H. H rotated by 90 goes to D, and D comes right back to where you started. And reflecting 90 gives you D, reflecting 180 gives you H, and reflecting 270 gives you U. So one thing that's kind of neat, this Cayley graph, it kind of shows you the vertices of a cube to represent the symmetries of a square. It's like a giant has come and stepped on our cube and smushed it down, and these end up being like the projection onto the plane of the vertices of our cube. Okay, now we're ready to complete this process with a then-do table. So just like we have a multiplication table or an addition table, we're going to build a then-do table for this set and algebraic structure that we're building. So filling in 0 is probably straightforward. 0 doesn't change the symmetry, so it just ends up copying the symmetry that's there. Okay, so I'll do one more row, and then you can fill in the rest of the table on your own. So let's do V. So if I'm going to perform V, I'm going to picture being located at V and then performing a 90. So performing a 90 takes me to U. Okay, so next I'll think about being at V once again, and this time I have to perform a 180. So I do two 90s. Maybe it would be helpful if in our picture we wrote the arrows. So doing the 90 is one blue, and doing the 180 is 2 blues, and that brings me to H. Okay, so the next part, V and 270. So I would be at V, and 1, 2, 3 90s makes 270, bringing me to D. So I'll put a D right there, and I'll remind myself that anytime I want to do a 270, I can do 3 blue arrows. Okay, so next up, it's a V followed by another V. So we're performing V followed by a V. So we start at V, and then performing a V brings me to 0. So I'm going to write a 0 right there. And next time we perform the V column, it's performed by a single red. Okay, so the next one that we're going to do is an H. And maybe this one is a little bit more complicated. How do we perform an H? So we need to track the arrows. So to perform an H, you start at 0, you do a blue, and then a red to land at H. So this one would be a blue arrow, and then a red arrow to land at H. Okay, so now let's perform V followed by H to fill in what goes right there. So starting at V and then performing an H is a blue, and then a red. So it takes me to 180. Okay, so next up is a U. Let's decide what arrows perform a U. So starting at 0 to decide what arrows perform a U, well, we would follow a red and then a blue. So a red one followed by a blue one. Okay, now we'll decide what happens when we do a V and then do a U. So starting at V and then performing a U is a red arrow followed by a blue arrow, taking me to 90. So 90 goes in there. One more to do. So a D. Let's think about how to perform a D. So to do a D, we would do a blue followed by a red. So let's write that next to the D. So a blue one followed by a red one. Okay, now if we do V and then do D, let's see where we end up. So V and then doing a D, so a blue and then a red, ends up at 270. So 270 goes in there. Okay, we'll do one more example before we pause the video. Let's say we wanted to do D and H. So I would start myself off at D and then do an H, and an H is a blue, and then a red. So it would end up at 270. Okay, so try to fill in the rest of the table, and I'll fill in the answers in just a moment. So pause the video now. Okay, so there's our table. Now we're going to ask ourselves some questions that work with this table, work with this operation. So first, is the set of symmetries closed under then do? Well, everything that we just filled in with that table is within our set S of symmetries, the 8 symmetries, so we can answer yes to this question, because the whole table that we just looked at is in S. Is the operation then do commutative? Okay, let's go back to our table and let's check. So if we draw our diagonal line, is it the same below the line compared to above the line? And maybe we notice right here, it's not the same. So V 270 is not the same as 270 V. Okay, so let's scroll back to where we were, and the answer to this question is no. Okay, now for associativity, can we move brackets? This one involves a little bit more thinking. Now, Unfortunately, we can't just glance at the table and decide if we can move the brackets. There would be a lot of different tests if we tried to do all the different possibilities, because there's 8 different symmetries and a lot of different combinations that could fit into this equation here. But the good news is, if we think a little bit closer about what then do actually means, we can decide that it is indeed associative. If we look at what these two statements actually mean, those expressions, it means first do xy and then do z. That's what we mean by brackets. But it results in doing x, then y, then z, because first doing xy results in doing xy. Now similarly, this next expression, it means first do x and then do yz. So if we first do x, that's fine, and then we do yz, and the yz results in doing the y and then the z. So in either case, you do x, you do y, and then you do z. And we can argue in this way that it is indeed associative. So the operation of then do is always associative. We get that order operation in a sense for free without a fancy proof, by just understanding what it is. Okay, next up, the identity element. Is there an identity element within the set? If there is an identity, find all of the inverses. Okay, let's go back to our table, search for an identity, and find the inverses. So the identity always comes up as a copying of the labeling column or the labeling row. And that, of course, occurs with 0. 0 leaves things unchanged, so 0 is our identity. And every time we see 0 pop up in our table, we have inverse pairs. So 0, 0, 0, and there's zeros along the main diagonal, building all of our inverse pairs. Okay, so we can go ahead and copy those down below here in problem D. So yes, 0 is the identity, and the inverse pairs from above are, and I've paired them together with that hidden then do symbol. So in between the zeros, there's a hidden then do, 0, then do 0. So we can actually say that these inverse pairs are all equal to each other. It's perfectly fine to say that symmetries are equal to each other. And in fact, they all equal 0, right? That's what the inverses do. They bring us back to 0. Okay, let's move on to part E. So part E says, find 2 elements that commute with all other elements. Now, in general, we found that our table was not commutative. We came up with an example of it not being commutative. But we're now going to try to search for 2 elements that we can switch order with. So we'll go back to our table, and we're going to look for a matching row and column. And maybe one of the easiest places to find that is always with the identity. This would always occur, that row exactly matches that column. So when you have 0 in an expression, you can move the 0 in a different order. It can commute with any other element. And if we search closely, there is one other element that does indeed commute with all the others. I'll let you think about it for just a moment before I give you the answer. You can pause if you like. So if you look closely, 180 has that same property. The row and the column matches exactly. So 180 can also switch order with any other symmetry that it might be then doed with. Okay, so we're ready to answer our question now. So we can say that if we write 0x, it's the exact same thing as writing x0 for every symmetry x. And the same goes for 180. 180x is the same as x 180. And once again, that holds for every single symmetry that's out there. And if you wanted to write this down as a phrase, we could say that 0 and 180 commute with all other elements. Okay, so now we've built a really complete picture of everything that we can do with symmetries. So let's try to put this to use. We can actually build equations and solve the equations with our symmetries in operation. We can do the solving because we have inverses. So we could search for what this x is. Let's go through a step-by-step process to try to solve some equations. Okay, let's remember what we just said about the 180. The 180 is kind of special because it switches order with any other symmetry that's out there. Even if we don't know what that symmetry is, we can say, oh, well, there's an x there and there's a 180. So we can switch the order if we like. We can write d 180 and x. What we're trying to do is isolate the x all by itself. Okay, so next we could perform the d and the 180. So if you do a d and then you do a 180, you get to a u. And then finally, we can apply the inverse to both sides of this equation to solve for x. So the inverse of u is u itself. So u gets applied to both sides of the equation. And what happens when we apply u to both sides of the equation? We get the identity on the left-hand side, and we get u 90 on the right-hand side, and the beautiful thing is our identity just disappears, and we successfully isolated x as u 90, and when we perform u 90, we get h. So one of the purposes to this exercise is to really understand that sometimes people say just move the u to the other side. We're not allowed to just pick it up and move it to the other side. What's going on is we're doing something that's exactly the same to both sides of the equation, and we're picking that thing to be the inverse, which gets rid of the u, gets rid of everything on the left-hand side, isolating the x by itself. Let's try another example. So this time we have hx90. So we can't do the trick of just move x to the other side of 90 because 90 doesn't commute with every single element in our set. So this time maybe we'll use the inverses right off the bat. So we have h, x, and 90, and u on the right-hand side. So the inverse of h is h. So we apply h on the left-hand side on both sides. And then we would apply the inverse to 90 on both sides to the right of it. So 270 and 270. And then the inverses magically make us just get an x all by itself. And then you would perform an h, a u, and a 270, and you would get 180 out of that. Okay, so finally, one more example. This time we have the exact same thing as above, except it's 0 on the right-hand side. So the very same procedure from above will isolate x. What we need to do is apply the h and the 270 to both sides. So we have h and then 270, and then performing an h and a 270 will give u as our final answer. Okay, so thanks so much for listening, and hopefully you've learned something now about the symmetries of a square, and we'll see you on the next one.